Hi, welcome back to Calculus. Today we're looking at section 8.6, numerical integration. So these are just a couple of ways that we have that we can use to approximate integrals. And so I'm going to show you the two methods. We'll do a problem using both methods, and then we'll look at some things involving the error as well. So let's say we want to integrate a function f of x from a to b with respect to x, and we're going to split it into n subintervals. So we have two ways we can approximate this using those n subintervals. The first is using what are called trapezoids. The trapezoid method says that t is equal to delta x over 2 times y sub 0 plus 2y sub 1 plus 2y sub 2 plus all the way up to 2y sub n minus 1 plus y sub n. So the first and last piece is the 0 term and the nth term. Both have coefficients of 1, everything else has a coefficient of 2. And it's worth pointing out, delta x here is b minus a divided by n. It's the width of each of those subintervals. Then we also have Simpson's rule. So I'm going to give you both rules, and then we're going to do a problem, the same problem using both of them. Simpson's rule, n has to be even. You cannot do an odd number of subintervals for Simpson's rule. That's okay, because we can always make an even number. For Simpson's rule, it's delta x, which is the same thing, b minus a over n. This time it's divided by 3, and then we have this substantially stranger little pattern. We still have y sub 0 at the beginning and y sub n at the end, but in between it goes back and forth between 4 and 2, 4 and 2, all the way down until you get back to y sub n. And that's why it has to be even, so that works out right. All right, so let's say that we wanted to do f of x is x cubed with 4 subintervals. You can see I'm going to integrate that from 1 to 2 here in just a second. Well, that's what I'm going to do. I'm going to integrate from 1 to 2. So with 4 subintervals, the first one, the 0 term, is at 1. The next one would be move over a quarter to 1.25, 1.5, 1.75, and 2. And since my function is x cubed, I cubed all of those values to get 1, 1.95 and change, 3.375, 5.35 and change, and then 8. Okay, so I have all these values ready because I'm going to be plugging them into these two formulas. So to integrate from 1 to 2, using trapezoids, I have 1 over 4, because again, that's my delta x over 2, just using that formula I had down there. And then you can see I plugged in all those values. There's that 1, 2 times y sub 1, 2 times y sub 2, 2 times y sub 3, and then 8 is the y sub 4. The end ends up equaling 3.79, and since you can find the actual value for this integral if you want, it's 3.75, we can get that this has an error of 0.04, which is really quite good. It's really very close. However, Simpson's rule does better here. So again, I'm just plugging these in. My delta x is a quarter. This time it's over 3. You can see I have 1, 4, 2, 4, and then back to just 1 of the 8s. Again, I'm multiplying by each of those y values in order. When you add all those up and do the multiplication, you get 3.75. And so in this case, Simpson's rule hit the answer right on the head. It was exactly right. So those are the trapezoid and Simpson's rules. Now let's take a look at a little bit deeper at some of the error. All right, so error. So it turns out that there are ways that we can estimate the amount of error that is present if we use either the trapezoid rule or Simpson's rule. So for error, we're going to call m an upper bound for the values of the absolute value of f double prime on the interval from a to b. So then we have these formulas for the error. The error from using trapezoids, or I should say its absolute value, because it could be negative, is that upper bound m times b minus a cubed all over 12n squared, where again a and b are the endpoints of our interval, and n is how many subintervals we're using. For Simpson's method, absolute value of the error for the Simpson's method is less or equal to m times b minus a to the fifth, all over 180 times n to the fourth. So let's just do this one. Let's do this problem with trapezoids, and then I have one last little tiny thing to look at on the next board. So I want to find an upper bound for the error using trapezoids and n equal to 4. We just did that problem, but let's look at it just in terms of the error. So I'm looking at the integral from 1 to 2 of x cubed dx. So my f of x is x cubed, which means its derivative is 3x squared, and its second derivative is 6x. Now, since we're on the interval from 1 to 2, and since this is just a linear function, its biggest value has to come at one of the endpoints. And in this case, you get your max at 2. Plug in 2 there, you get 12, and that's going to be our m. Remember, this m is the maximum for the second derivative, or the absolute value of it, rather, in case you have negatives. And so then I just plug in my 12 for m, 2 for b, 1 for a, and 4 for n, and I get that my error has to be less than or equal to this 116. So there we go. That's how we find errors, or estimate the errors, I guess I should say. And now what happens if we want to be assured that our error is as small as we could possibly want it? So let me change the board. All right, so our last bit is just to answer this question. Using Simpson's rule, how many subintervals would be required to have error less than 10 to the negative fifth for that same function we've been working with, that x cubed from evaluated from 1 to 2? So 10 to the negative fifth is the same as 0.00005. And all I'm going to do is I know the formula for Simpson's rule. It has 12 on the top, or I'm sorry, 12 is our m, so that's why that's on the top. B minus a to the fifth, all over 180 times n to the fourth. So I'm going to take that and set it to be smaller than the error I want. Then I can divide both sides by the nasty decimal, multiply by n to the fourth. That gets me to here. So I have 12 over 180 times 0.000, so I'm going to put down a 0 there. Be careful. Another 0, there we go. 0.00005. And then if I take its fourth root, I get that n needs to be bigger than 6.04. Now, since this is Simpson's rule, n has to be an even number, and it's got to be bigger than 6.04. So in this case, n has to be at least 8. If this were our answer using trapezoids, then it would have to be at least 7, because we have to get past the 6.04. So 6 isn't big enough, but 8 is, because again, even numbers for n here, since it's Simpson's rule. So there you go. That's Simpson's rule and trapezoids and some estimations. Have a good day.